Hello and welcome everyone. I'm Hagen Neugebauer from FACCTs, and today I'm going to tell you something about ORCA meeting Python and neural networks. We will start with Python. So why are we interested in Python? Python is a powerful tool for automatization. Many ORCA users are already familiar with Python and using it to script their workflows or parsing their output. The Python ecosystem offers many tools for computational chemists, for example, RDKit, NumPy, and Pandas. An easier integration of ORCA into the Python infrastructure is desirable, and therefore we present the ORCA Python interface, or short OP. OP is an open source project created by FACCTs, and it can write ORCA input files, handle the execution of the ORCA job, and parse the output, all separately and all in Python. The source code is available on GitHub, and we will now take a look at a simple DFT energy calculation using OP. We start by importing the OP classes into our Python scripts. Here we import the calculator, which basically drives the entire calculation. Then we need some input keywords where we import simple keywords with DFT context, and we want to set our molecular structure, so we import the structure. Then we prepare the calculation by setting up the calculator, supplying it with a base name, and next we read the structure from an XYZ file. Here an external struct.xyz file is read, which contains a water molecule that is simply read. So now we add what type of calculation we would like to do. So we add a simple keyword, DFT R2scan3c. This is a composite DFT method that comes with a predefined basis set that should also not be changed. So we are already good for our calculation. Note that we have these input classes which are already provided for simple keywords and also for the most important blocks. And these enable to get the output with auto-completion in your IDEs. So when you use PyCharm or Visual Studio Code, you can get auto-completion. Now we want to run the calculation. For that we use the .writeInput method and the .run method. After that, after the calculation has finished, we can get the output with .getOutput, and we can check the output if it has terminated normally. If it has terminated normally, we can parse it and then print the final energy in hardtree, which is the property we are interested in this example in here. And you can see that the output is a Python dictionary, which is obtained by parsing the improved new property JSON file. Let's take a look at the complete script. We have the imports, where we import a calculator, some input keywords, and the structure method, the structure class. And then we set up our calculator with a base name, a structure, and the type of calculation we want to do. We perform the calculation and get the output, where we can check if it terminated normally. This is a relatively simple example, and we prepared some more elaborate example in the OP tutorials for you. Here we have some Jupyter notebooks to showcase various applications that can be done with OP. These include extracting quantum mechanical properties for machine learning, for example, the OMOL25 properties with the level of theory used in that set, and some of the properties extracted in that set. We also have a conformer generation and re-ranking notebook where we generate conformers sample with RDKit or with Goat and then re-rank them with DFT single points. We also have various energy decompositions as notebooks, for example, the local energy decomposition, the covalent variant of that, and the atomic decomposition of the London dispersion energy. We also have a notebook on the visualization of atomic charges and Fourier indices, and we have more upcoming notebooks that will be included later. For example, we have one where we use OpenCosmos to generate a sigma profile and calculate solubilities. We also have one in the pipeline for OrbNet-like calculations, so stay tuned for those. These notebooks are available on GitHub, but also on our FACCTs website to look at them. And we will look at the initial ORCA Python interface tutorials. And here we can take a closer look at one specific example, the conformer search. And we can directly see one advantage of using the Python infrastructure. We can benefit from visualization techniques. Here we have Py3dmol, and we can directly visualize the conformer ensemble within our notebook. Here this is just a small molecule, not many conformers are included, but you can visualize them. The small molecule is only used to keep the computational costs low, but if you take a larger one, you can also visualize these conformers using Py3dmol. You can also make plots of your re-ranking procedure when you compare your force field energies with your DFT energies. You can directly plot this relative energy plot here shown on the right with matplotlib. And when you change the molecule you use, you can get also this plot for your other molecule. We also have a notebook on the local energy decomposition, also in the relatively new fragment pairwise scheme. Here we have a simple example of methanol interacting with 3 water molecules. We assign fragments with the autofragmentator by Nicolas. We have then 4 fragments, 1, 2, 3, 4. And the interaction energy is calculated between methanol and the water cluster. The total interaction energy is minus 20.3 kcal per mole. And the LED calculation is performed within ORCA, but the post-processing can be done within this notebook. And we can directly plot the results as heat maps, as shown below. And here you can see that fragment 1 most strongly interacts with fragment 2 and fragment 4, which are its nearest neighbors. So this is to be expected. We also have the covalent version of the LED, where fragments can be connected by covalent bonds, and the heat map is shown below. Here the interaction energy between the 2 ethane molecules is much smaller, and you can not only look at the total LED contribution, but you can also look at the other contributions from the LED. If you're interested, you can just download the notebook and look at the different contributions. Last but not least, we have the notebook on the atomic decomposition of London dispersion energy, ADLD. And here the calculation of the atomic contributions is done within ORCA, but the post-processing to dispersion densities is done within the notebook. And you can directly visualize them in the notebook as shown on the right here. Here we have the ADLD with D4 and HFLD for adamantane dimer and a cobane dimer. And the white-red gradient shows the strength of the dispersion density, and the more red you have, the more London dispersion interaction there is. So additionally, also a cube file is here generated on the fly for further post-processing. With that, I'm already at the end of my OP part of this talk. So OP can be obtained from GitHub. Check out facts/OP. We hope that it will help Python users to script their workflows and to obtain the output of these workflows. And OP is under active development, so we would be really happy if you give us your feedback, and you can feel free to contribute. The OP team consists of Tim Tetenberg, Dr. Markus Bursch, Nakul Santosh, Shizhao Yu, Christoph Plett, and myself. Next, we come to the neural networks. So, as many of you very likely know, neural network potentials have become better and better over the recent years. This is also with the help of ORCA reference calculations. For example, the AimNET or the OMO25 models are prominent examples, and these are very promising tools for modeling chemistry with low computational costs. They can be used from within ORCA using the ExtOpt feature with !ExtOpt. Then you give in the method block the path to your script. The script has to call the neural network potential and calculate energy and gradient. And this can then be used in optimizations in ORCA. Scripts for these neural network potentials are available on GitHub. Check out facts/ORCA external tools. And there you will find various scripts, including neural network potentials and semi-empirical methods For example, you will find the AimNET2, UMA, the universal model for atoms. You can find MOPAC, where you can do PM6 or PM7 calculations, and MLAtom will be added also soon. So why should you use these neural network potentials from within ORCA? You can use the ORCA optimizer. So if you want to optimize an RNA ligand cutout using AimNET2, you can do this, use the ExtOpt keyword, give the path to your script, and then you can additionally, to just a regular optimization, also perform constraints. In this case, for this RNA ligand cutout, when you have the normal cutout on the left and you do the optimization without constraints, you lose a lot of structure from the backbone. When you constrain the backbone, this does not change. So this allows relaxation while preserving specific structural features, for example, the backbone in an RNA. Another more elaborate workflow is using neural network potentials to search for conformers using ORCA's GOAT conformer searcher. Typically, conformers are searched with relatively cheap methods like semi-empirical methods or force fields, but often due to lack of accuracy, re-ranking with DFT methods is required. And this can be expensive, especially if you have to choose large energy windows for re-ranking your conformers. So here, using the neural network potentials in your generation of conformers can potentially save you time for subsequent re-ranking steps, or even find you better conformers. Especially interesting here is the UMA ORMOL25 model, because it is available for many elements, all elements up to cardinal number 83. And this allows also to run GOAT with a neural network potential for organometallic complexes. Here we have the carbene iodine palladium complex, and here the ensemble is visualized, which was generated with GOAT using UMA and ORMOL25. You can also use the nudge elastic band method in ORCA to search for minimal energy pathways and transition states. Here we have, for example, the hydrolysis reaction of methyl acetate, and you can see that this gives a nice path calculated with UMA ORMOL25. And you can even go further and use ORCA to optimize the geometry of the transition state and calculate the frequencies and verify the imaginary mode of the transition state. So this is possible with the numerical Hessian in ORCA. So all ORCA optimizer features are available with ExtOpt. For example, the NEB, the LOpt, GOAT, and various scans and constraints. And feel free to try out to run neural network potential calculations via ORCA. With that, I'm already at the end of my talk. Thank you very much for listening. If you're interested in the ORCA Python interface or into the neural network potentials, please visit FACCTs at GitHub and check out our repositories.